what I want to talk about before we do that is the difference in the types of geometries depending on the structure. So what we've been looking at currently is the electron domain geometry, where we take every electron domain into account that is around that central atom. So this is going to be our lone pairs and our bonds. Okay, when there's a lone pair on the central atom, that's going to change things a little bit. So another geometry that we look at is the molecular geometry. And this is strictly looking at the arrangement of the bonded atoms. So this is where we omit lone pairs. And as we'll see, even though we're omitting them from determining the geometry, they still play a role in how the angles are calculated. So in an ABX molecule, the bond angle is the angle between two adjacent AB bonds. Okay, so we talked about that. Linear has 180, trigonoplanar has 120, tetrahedral has 109.5, trigonobipyramidal is the one where we have axial and equatorial atoms, so they have two different angles of 90 and 120. And octahedral has 90 degrees amongst all of our adjacent atoms. Okay, so when the central atom in an ABX molecule has one or more lone pair, the electron domain geometry and the molecular geometry are not going to be the same, because the molecular geometry only cares about bonded atoms. Okay, so here we have ozone again, O3. And we said that this has 3 electron domains. We said that earlier in our lecture. So if it's 3 electron domains, the electron domain geometry would be trigonoplanar. Okay, because we have an electron domain here, here, and there. When we go to molecular geometry, though, we only care about the atoms that are bonded. So we only care about this bond and that bond, which, looking at the difference, we see is not the same shape as a trigonoplanar. Now, what I said before, where the lone pairs still play a role, that's because they're still here. Okay, I'm going to draw them here. And they're still affecting the bond angles, right? There's still an angle between them. It's not like when we go to do molecular geometry, the lone pairs disappear and I'm left with that. Okay, it doesn't turn to linear. Okay, so the lone pairs still play a role, but all we're looking at is where the bonds are going. So we're looking at where the bonds are in relation to that central atom. Okay, so the lone pairs don't just disappear, they still play a role. We're only looking at where the bonds are in that specific atom, molecule. So when we're looking at the example of ozone here, let me erase some of these lines since it gets a little confusing here. Okay, we have our 2 bonds. This creates a structure that we call bent, okay, because it looks like a bent molecule. It looks like I took it and I bent it. Okay, so when we have an electron domain geometry of AB3 and it has 1 lone pair on the central atom, the molecular geometry then becomes bent. Now this applies to each of our geometries. So what we're going to do next is go through each geometry and talk about how adding lone pairs affects the structure and the molecular geometry and the specific names we have for the molecular geometries. Okay, so we first looked at our trigonopyramidal. Our linear molecules will never have lone pairs, so don't worry about linear, it's always going to be linear. Okay, there will be no lone pairs there. Next up we have tetrahedral, so this is going to be our AB4. Okay, so our electron domain geometry for all of these is still going to be tetrahedral, but now we're going to add lone pairs. So when I add 1 lone pair, This is going to be one lone pair, 3 bonds. We can see that we're still forming that tetrahedral shape. You can see that by the little green triangle here. Okay, we're still forming that tetrahedral shape when one of those bonds is replaced with a lone pair. But if I look at just the bonds, okay, they're still creating a triangle, but they're out of plane. Okay, they are no longer in plane like trigonal planar would be, okay, because those lone pairs are still playing a role, they're still affecting the repulsion of the electrons in those bonds, okay, so our molecular geometry shape is now trigonal pyramidal. Trigonal still meaning 3, there's 3 bonds that are playing a role. Pyramidal for this means that they are out of plane, making a pyramid. Okay, so they kind of make a little pyramid there. It's smaller in comparison to the other ones that we looked at, but it's still a pyramid because they're coming out of plane. So that's one lone pair. We can also replace another one of these bonds with another lone pair, so that brings us to our next example where we have 2 lone pairs and 2 bonds. Okay, this is the structure of water. So water's electron domain geometry is tetrahedral. Okay, it still has 4 electron domains around it. 2 of those just happen to be lone pairs. So if we look at just our bonds, okay, we see that we have 1 bond and 1 bond. Okay, so our 2 bonds are now making up another bent structure. So we have 2 versions of a bent structure. We differentiate them because this bond angle is 109.5. So they're still keeping a similar bond angle to their original electron domain geometry. Okay, so that's how we can tell the difference between our bents. Our bent up here, this has an angle of 120 degrees. Okay, so when we have 2 lone pairs and 2 bonds, that's going to be a bent geometry. It still looks like a bent molecule. Okay, let's move on to our AB5. This one we're going to have even more because with each new bonding group or each new electron domain, we can replace it with more lone pairs. So we have AB5, and again, this is going to be our expanded octets. We can still have expanded octets even if some of those electron domains are lone pairs. Okay, we can still have expanded octets for AB5. Okay, so our electron domain geometry for these with 5 electron domains is still trigonal bipyramidal. Remember, tri for 3, bi for 2 equals 5. Okay, so let's add 1 lone pair and 4 bonds. So instead of having 5 bonds, we're going to replace one of those with a lone pair and have 4 bonds left. Now, we said that AB5 molecules have 2 different types of atoms. We have our axial and our equatorial. When we are adding a lone pair onto our AB5s, okay, the lone pairs are going to go on the equator first. And this is so that we can have our best amount of repulsion. Okay, so if we put them up on an axial, which is the example we have here, okay, there are now 3 90-degree angles that are repelling those lone pairs. Okay, lone pairs are strictly electrons. They're not wrapped up in a bond being shared or anything like that. So they want to repel them more. We don't prefer lone pairs. Okay, so by adding it to the equatorial, there's only two 90-degree repulsions in that molecule, so that's limiting our number of repulsions, which is preferred. So we want to limit our repulsions with lone pairs. Okay, so that lone pair goes on the equator first, okay, on the equatorial atoms first. So when we have 1 lone pair and 4 bonds, our molecular geometry becomes a seesaw. And if you were to spin this, I can try to draw it the best I can. So here's our central. There's one, there's two. And then it has two going off this way. That's just if I like rotated this. Okay, we see that one linear portion here is now turned here. Okay, this literally looks like if I put a person here and a person here, it looks like a little seesaw. So again, we're not that creative with our naming, us chemists. So that is a seesaw shape. Okay, so that's one lone pair. What if we bumped it up to two lone pairs? So that's our next example down here. So we still have a trigonal bipyramidal. These are all trigonal bipyramidal. We just have two lone pairs and 3 bonds. So again, that's still equaling 5. Okay, again, our lone pairs are going to go on the equator. Okay, that's just minimizing our repulsions. Okay, so the molecular geometry, if I were to just look at the bonds, this is now called a T shape because it literally looks like a T. All of those atoms are in plane with each other. Okay, we're now in the same plane, so they make a T shape. Again, not creative with our names. And finally, our last example has 3 lone pairs and 2 bonds. So our last lone pair gets added to the equator. Okay, and my bonded atoms now are just in a straight line, which is linear. So just like we started with. So as we add more and more lone pairs, we're simplifying that structure more and more, and we usually end up in either a bent or a linear structure. Okay, so that was all of our AB5s. Okay, so we went from 1 lone pair, 2 lone pairs to 3 lone pairs. Okay, we went seesaw, T-shaped to linear. Now we're going to look at our AB6. So AB6. So our lone pair gets added on. It doesn't matter where because all of the bond angles are the same. Okay, so we went from octahedral when we added that lone pair. So now we have 1 lone pair and 5 bonds. So still 6 electron domains for an octahedral electron domain geometry. For our molecular geometry, this now becomes square pyramidal because we make a square which then form a pyramid. Okay, so we just removed that other half of that pyramid by removing that lone pair. So if we're looking at just where the bonded atoms are, it makes a square pyramidal shape. So that's 1 lone pair. Next up, we have 2 lone pairs and 4 bonds. Okay, so it's still octahedral for its electron domain geometry because it still has 6 electron domains. But now our molecular geometry, if we look at just the bonds, we have a square planar structure. Okay, this is because the lone pairs are actually being added 180 degrees from the other ones. So this is where this is the only step where adding that lone pair matters. Okay, so they're going to add to the opposite side of each other to minimize those repulsions again. So because we added them down here first, the next one are going to go up here. Okay, they can't go here or anything like that. So by putting the lone pairs 180 degrees from each other, we're minimizing the repulsions both with the bonds as well as with the other lone pair. Okay, so this creates, again, we keep that square, but now we get rid of the pyramid portion. So we got rid of this portion here. So we're left with a square. All of our atoms are arranged in a square, and they're all in plane. So we get square planar. Square because there's 4 of them, planar because they're all in the same plane. Okay. Our last 2 examples are similar to what we saw. Oops, let me get rid of this. We don't need that yet. Ignore this. We don't need this portion yet. Okay. Sorry, that's a typo from a previous class. Our last two examples are what we saw before with the AB5 notation. So if I added another lone pair onto here, so if I created this to be a lone pair instead of a fluorine, okay, that would get rid of this guy. And our shape would then be in a T, so we get another T shape. So this is 3 lone pairs and 3 bonds. Okay, that's T-shaped. So I have 3 bonds, they're going to form a T shape. And then if I were to get rid of another one, so if I were to add another lone pair, I would add it directly across. Okay, that would get rid of that fluorine, and I'm left with a linear structure. Okay, so this would be 4 lone pairs and 2 bonds. Okay, so you see that we keep simplifying, and then the shapes start to be the same. So our atoms that obey the octet, they're going to end up in a bent structure, and our atoms that are expanded octets, they end up in a linear structure. So now I've provided a table. This table, I believe, is in your note pack as well as in our test taking materials. It's given to you on your ALEKS exams. You're given this chart here. We haven't learned about this column yet. Don't cross it out on your own. You're going to need it for this chapter, but for right now I'm crossing it out because you won't need it right now, so it doesn't make sense to you. Okay, you will need it, so don't cross it out on your own, or I'll uncross it out. Okay, so we don't get confused, but we don't know what that column means yet. We will learn about that in this chapter. But this tells us a guide of all of our different geometries. Now, this column here, this is just our electron domain geometries. So if I'm looking for just electron domains, I only care about this column because it directly relates the electron domain number to that. Okay, so if I'm asking for electron domains, I don't care if they're bonds, if they're lone pairs, whatever, I am asking strictly about that first column. If I'm talking about molecular geometries and we start adding lone pairs, well, then we're talking about everything here. Okay, so this is when we start adding lone pairs. Okay, and I'm asking about the molecular geometry. We can have times where the electron domain geometry and the molecular geometry are the same. That would be when we don't have any lone pairs. So the only time they are the same is when there are no lone pairs. Okay, which is the step right here. So when we're determining our geometries, the first step that we want to do is draw our Lewis structures. We have to make sure we have an accurate Lewis structure because we have to account for lone pairs on our central atom properly. If we're missing those lone pairs or have too many, then we're not going to have the correct structure or the correct name. We then want to count the number of electron domains, both lone pairs and bonds, in order to determine the electron domain geometry. Okay, so that's again just talking about this one. That's our step 1. If there are no lone pairs on the central atom, then the electron domain geometry is going to equal our molecular geometry. They will be the same. But if there are 1 or more lone pairs on the central atom, then you have to use the chart to find the molecular geometry. So that's all here for step 4. So if you have lone pairs, you're going to want to look in that portion of the chart when I ask specifically for the molecular geometry. So if we're asking for electron domain geometries, it doesn't matter if there's bonds versus lone pairs, it's not going to change the geometry. But if I'm asking about the molecular geometry, the lone pairs matter. Okay, so let's practice that. So we have PCl3 is an industrial chemical used in many herbicides and insecticides. The electron domain geometry of PCl3 is what? And the molecular geometry is what? So let's look back. Our first step is to draw the Lewis structure and then count the number of electron domains, and that's going to give us our electron domain geometry. So let's do that. PCl3, draw our Lewis structure. So phosphorus gives us 5 electrons, and then we get 3 times 7 from the chlorine, so we have 26 electrons in total. So we do phosphorus with 3 chlorines around it, so that uses up 6 electrons. I have 20 left. I need to complete my octets on my chlorines. That uses up 18. I have 2 electrons left. I'm going to put those right on my phosphorus in order to complete my octet. Okay, so that is my structure here. Now again, this is a perfect example of why we need to follow our Lewis structure rules for drawing this, because some students look at this and say, oh, it's PCO3. Done. Which is incorrect because you're not accounting for your lone pairs. Your lone pairs are going to be important. Okay, so our electron domain geometry for this one, well, if I have a bond, I have 3 bonds and 1 lone pair, that means I have 4 domains. Okay, so 4 domains for the electron domain geometry is then tetrahedral. For the molecular geometry, we have 3 bonds, 1 lone pair. Well, let's go to our chart. So, I have 4 electron domains, so I know I'm in this column here, or this row. Okay, so my electron domain geometry was tetrahedral. We just determined that. I now have to look at how many lone pairs I have. Well, we said we had 3 bonds and 1 lone pair, so 1 lone pair is here. That corresponds to this box here. Probably shouldn't use blue because it's a blue box. Okay, so our molecular geometry is trigonal pyramidal. Okay, so we see that. If we compare our structures, we have 1, 2, 3 bonds and 1 lone pair. Okay, so this is trigonal pyramidal. So our best answer for this would be C, tetrahedral and trigonal pyramidal. Okay, let's keep practicing. So, for the following Lewis structures, determine the electron domain and the molecular geometries. Okay, so for our first molecule here, we have 1, 2, 3, 4 electron domains. Okay, all of our angles look correct. We have 109 degrees between all of those. So our electron domain geometry is going to be tetrahedral. Okay, and our molecular geometry is also going to be tetrahedral. Okay. Now, what I want you to do for these next 3 is use your chart from your Notepack or your test-taking resources and determine both the electron domain and the molecular geometries. I will point out on our third structure here, the only way I'm able to get these bond angles the way they are is if we have a lone pair there, which they don't show. Okay, the rest of these are all at typical angles, so we have 120 and 90, so there aren't any lone pairs on those. We know that because of the angles. Okay, for this one we knew that we had to have a lone pair. For this third one we knew we needed to have a lone pair because I have 90, 90, 90, and 90, and 90, which is not a valid structure, so we have to put our lone pair there. So keep that in mind as you go to answer this question, that there is a lone pair on the bottom of that structure. Okay, our next example has 1, 2, 3 electron domains. So our electron domain geometry is trigonal planar. Okay, we know this because we have 3 electron domains and they're all in the same plane and they make a triangle. Okay, so they're all in the same plane. Okay, since there are no lone pairs, the molecular geometry is also trigonal planar. Okay, our next one, the one with the secret lone pairs. Our electron domain geometry, well, we have 1, 2, 3, 4, 5, 6 electron domains. Those lone pairs count as an electron domain. So this is octahedral. 6 electron domains is octahedral. If we have 5 bonds and 1 lone pair, that means our molecular geometry is square pyramidal. Let's look at that. I'm going to erase my lone pairs for this because they don't matter for our molecular. I make a square out of my base, and then they all connect to the top to make a pyramid. So square pyramidal. Our last one, the electron domain geometry, well, I have 1, 2, 3, 4, 5, 6 electron domains again, so this would be octahedral. And the molecular geometry is the same because there are no lone pairs. It would also be octahedral. Okay, let's keep going. For the given molecules, draw the Lewis structure and determine the molecular geometry of each structure. Okay, so what I want you to do, pause the video, draw out your Lewis structures for these first, then try to find your molecular geometries. This first structure, we need to draw our Lewis structure properly. We have to count our electrons. There's 34 electrons total in this structure. So we have the selenium in the middle. We have the 4 fluorines around it. Okay, and those all have lone pairs on them. I think for time purposes, I'm not going to draw my outside halogens with lone pairs anymore, just for this portion when we're practicing, okay? But when we do that, we use up 32 electrons, so I have 2 electrons left over. So they are going to go on the selenium as a lone pair. So that means I have 5 electron domains, 4 are bonds, 1 is a lone pair, which corresponds to a seesaw geometry. Okay, so that's 4 bonds, 1 lone pair. That's a seesaw. Okay, this is why following our Lewis structure rules is very important, because our structure or our formula doesn't tell us anything about lone pairs. So if we just go off of our formula and say there's 4 fluorines coming off of that, therefore it's tetrahedral, then is not correct. Okay, so let's look at the next one. SiCl4, there's 32 electrons here. We have an Si with Cls. Imagine that those Cls all have lone pairs around them, but for time purposes, I'm not going to draw them. There's no lone pairs on my silicon, so I have 4 bonds, no lone pairs, making this tetrahedral. Okay, we did PCl3 before. Do you remember what that one was? Did you look back in your notes to show that it was PCl3 Imagine some lone pairs on there, but then there was the lone pair on the phosphorus. Did you remember that? Okay, so that one is going to be 3 bonds, 1 lone pair, leading to a trigonal pyramidal. Okay, we did that one earlier. Okay, and then we have XeF4. So this one, lone pairs matter. We have Xe. I'm going to try to draw this as dimensional as I can. Okay, then we have 2 lone pairs on the xenon. Did you get the 2 lone pairs on that xenon from your count? Okay, so that's 2 lone pairs, 4 bonds, which gives us square planar. Okay, square planar because these fluorines all form a square and they are in the same plane. Okay, so that's octahedral for our electron domain geometry, but since I have 2 lone pairs, that becomes square planar. Okay. Now, let's talk a little bit about bond angles and the effect that lone pairs and multiple bonds have on those angles. So we said that they don't matter for terms of electron domains, which is true, but they do change our bond angles a little bit more because they have a little bit more electrons. So if you think about it, lone pairs are going to take up more space than bonded pairs of electrons, right? Because they're in kind of their own little bubble. They're not being shared or anything. So they are just by themselves. So they take up more space. And multiple bonds repel more strongly than single bonds because they have more electrons. Right? So if you look at this structure here, I have 2 electrons in that bond, 2 electrons in that bond or that domain. But in our double bond of C double bonded 2 and O, I have 1, 2, 3, 4 electrons. So if I'm looking at electron domains, I have 4 electrons in this domain, but only 2 here and 2 here. So they're going to repel much more than if that was just a single bond. Okay, so we see that the bond angles become affected by that fact. So let's start at the beginning. We have NH3. So this would be tetrahedral for an electron domain, which gives us an angle of 109.5. But because I put a lone pair on there, they're going to force, this lone pair is going to force these bonds closer to the other bonds, creating a bond angle of 107 degrees C, or degrees Celsius. We are not doing temperatures, my goodness. So 107 degrees. Okay, it's not a big change, it's not a huge change, but it changes it. Okay, so you have to remember that. For this one, we have SF4. Okay, we have a lone pair, again, on our central atom there. So what that's going to do is start to repel these bonds, those F bonds, but then because those are being repelled, it's then going to repel these as well. Okay, so we went from having 180 degrees now to now having 170 degrees, and from having 120 degrees to having 101 degrees. Okay, so they do change it. Now, I'm not looking for you to memorize the specific numbers, so okay, so I don't need you to remember that 180 turns into 173.1. You do not need to remember that. What I want you to understand is that because lone pairs take up more space, they cause a larger repulsion, therefore changing those bond angles, making them smaller. Okay? So the same thing goes for our BF5 here. With our double bond example here at the end, okay, with CH2O, what normally would be 120 degrees, so this is normally 120, is now 122 because the 4 electrons in these bonds are pushing these down more. Okay, so it's then decreasing this bond, which was 120. This is now 116. Okay, so the bonds between the hydrogens, okay, it becomes smaller because the bond between the oxygen and the hydrogen becomes larger. They're repelling it more. Okay, so we just have to remember that because of those repulsions, those angles are changing.